In this video, we're going to go over how to calculate equilibrium constants for weak acids and weak bases. So for weak acids, to describe the equilibrium constants specifically for weak acids, we're going to use Ka. So that's the acid ionization constant, and the equilibrium law expression for it is going to be this. So our products are hydronium and then whatever the conjugate base of the acid is divided by the acid. So let's write a little note here that just means that this little a here stands for acid. Meanwhile, for weak bases, the equilibrium constant, we're going to be using Kb to talk about the base ionization constant. So B just stands for base, as in weak base. And the equilibrium law expression for that is going to be the concentration of hydroxide multiplied by the conjugate acid to the base divided by the concentration of the base. So in this first example here, we're asked to calculate the equilibrium constant for hydrozoic acid. Okay, so that's HN3. So just be very careful with this because some students get this mixed up with ammonia. So this is not the same as ammonia, which is NH3 instead of HN3. Okay, now since we're dealing with an acid here and they're asking us to figure out the equilibrium constant, we're being asked to figure out what Ka is equal to. Now we're told that hydrozoic acid has a concentration of 0.015 moles per liter and a pH of 3.28. Write the equilibrium expression for the acid as part of your answer. Okay, so for this, with dealing with either weak acids or weak bases, you are going to want to work with ice tables here. So let's get it started by writing out a balanced chemical equation. So we have hydrozoic acid. Now, this question doesn't mention that hydrozoic acid is reacting with anything, so then because of that, we're going to react it with water. So this is going to be a modified Arrhenius equation. All right, so I'm just going to write out what I just said up here. So when there's nothing else mentioned in the question that one substance in the question is reacting with, then you just react either the weak acid or the weak base with water. It just depends on what the question's talking about. Okay, so the reason why I use these equilibrium arrows is just because hydrozoic acid, if you look on page 8 of your data booklet, hydrozoic acid isn't one of your strong acids. Therefore, it is a weak acid, and whenever you have a weak acid, you're always going to use these equilibrium arrows there. Now for predicting our products here, since this is acting as our acid, remember A for away. So that means this hydrogen is moving away from hydrozoic acid. So with predicting our products, or I'll write the H plus right there. So for predicting our products, the first one, I'm just going to imagine hydrozoic acid just with one less hydrogen. So that would be N3 with a 1 minus charge. Okay, so how I got the charge is hydrozoic acid started out with a neutral charge. We lost a +1 charge. So if I clean this up, 0 minus 1, that's equal to -1. That's how I'm getting the charge here. So remember, you do have to be able to predict products as well as the charges on those products. Now our other product, that's going to be water just with one more hydrogen in it. So that'll be H3O plus, so that's hydronium. Okay, and how I'm getting the charge for hydronium is water started out with a neutral charge. We gained a proton, or we gained an H plus ion, so that's how we're getting +1. Okay, so now let's draw out our ice table. And I'm going to draw a thicker line underneath the equilibrium arrow just so I can separate my reactants from my products here. Alright, so we're told that hydrozoic acid has a concentration of 0.015. So that's going to be its initial concentration before this reaches equilibrium. Now with water, since it's the only liquid in this equilibrium, remember when you only have one liquid, you do not include it in your equilibrium law expression, so we don't need to write any information in this column here. Now, moving along in the initial row with this N3 1 minus, as well as our hydronium ion, since the concentrations of them are not mentioned in the question, that means we can assume that they are both 0 moles per liter. Now for the change row, if we look at the initial row, that tells us which reaction is favored. So since we only have reactants and no products, that means that what the equilibrium is gonna, or what the system is gonna wanna do in order to establish equilibrium is it's gonna wanna favor the forward reaction here. So if you want a visualization of how to tell whether the forward or reverse reaction is favored, what you can think of is sort of like a seesaw here. Okay, so over on the left side here we have our reactants, and over on the right hand side we have our products. Now in order to achieve equilibrium or a balance on the seesaw, right, the ball has to move towards the right, or it has to favor the products a bit in order to get the seesaw to be balanced. So that's more of a visual way to figure out whether the forward reaction or reverse reaction is favored. And because of that, we now know, okay, the reactants are being used up and the products are being produced. So what that means is in the change row, I'm going to go minus X. Okay, so in my balanced chemical equation, there's a 1 coefficient here, so that's why it's just minus 1x here. Now we're producing products here, so I'm going to go plus x plus x, and both of our products only have a 1 coefficient in front of it, so that's why I'm only adding 1x to both the N3 as well as the hydronium ion. Now in our equilibrium row, I'm going to be using the I plus C is equal to E, so 0.015 plus negative x, that's going to be 0.015 minus x is going to be equal to the equilibrium concentration of hydrozoic acid. Meanwhile, doing the same thing for N3 and hydronium, we'll get x because it's 0 plus x for both of them. Okay, so after our ice table, we need to figure out what exactly x is. Now, how we can do that is because we've been given the pH for this system here, we can use that to determine concentration of hydronium, which would then help us to figure out what x is. So since we have the pH, we can use that to find the concentration of hydronium and therefore x. So remember the formula that we use to find hydronium from pH would be 10 to the power of negative pH. So then let's substitute in our value for pH, which is 3.28. So negative 3.28. So then I'm going to put that in my calculator here. So second function log to get the 10 to the power of negative 3.28. So most common mistake here is to forget the negative. If you don't put that in, you're going to get a weird number. So concentration of hydronium is going to be 5.2480, goes on forever, and then times by 10 to the power of negative 4. Again, the most common mistake with recording numbers like this is that students forget to write the times by 10 to the power of whatever exponent it is. So this is in moles per liter. Okay, so now that we have the concentration of hydronium, remember that the concentration of hydronium represents X. So then moving on in this question, since we didn't have to figure out all of the equilibrium concentrations of each species, instead we need to figure out what the equilibrium constant is for hydrozoic acid. So let's write out the equilibrium law expression. So Ka, because we're talking about the equilibrium constant for a weak acid. So I'm just going to use this to help remind myself to put the products in the numerator. So we have the concentration of N3 times by concentration of hydronium divided by concentration of hydrozoic acid. So remember that Ka, or any equilibrium constant, is only going to apply to the equilibrium row. It does not apply to the initial row or the change row. Okay, so we had a value of x for the concentration of N3 1 minus. I will plug in my value for x in a second here. So we have x times x divided by 0.015 minus x. Okay, so again, all of these values here, I'm only getting from the equilibrium row here. Now, since we know what x is, I'm first going to clean this up a little bit and then substitute in my value for x. So I'm cleaning this up, just going x times x. That's just x squared. And then let's plug in our value for x. So just remember that I am using the raw unrounded answer when I am calculating my equilibrium constant for this weak acid. So how I'm going to put this into my calculator here is I'm going to go bracket second function answer, close the bracket, divide by 0.015 minus second function answer. Hang on 1 second. Oh, made a little mistake here. So I gotta put a square right here. The square is coming from right here. I just accidentally missed it. So let's just clear this line and then try it again. So second function answer squared divided by 0.015 minus our answer, close the bracket, hit enter. So we're going to get 1.9027, goes on forever, times 10 to the power of -5. Now remember, with equilibrium constants, they do not have units. So now what I'm going to do is I'm just going to round this off to the appropriate amount of sig digs. So it looks like this number that we've been given, since it's concentration, and the word concentration does not have the letter P in it, so we look at the entire number. So this has 2 significant digits to it. Now with pH, since it does have a P in it, we're going to only look after the point to determine sig digs. So this also has just 2 significant digits here. So my final answer needs to be in 2 significant digits. So I'm going to count, since it's Ka, or the equilibrium constant, that doesn't have the letter P in it. So I'm looking at the entire number to determine sig digs. So 1, 2, there's my cutoff line. So our Ka is 1.9 times 10 to the power of -5. Remember that the times by 10 to the power of whatever exponent is not included in sig digs for any number. All right, and that's that question finished there. So just as a reminder, this did have 2 questions in it. So 1, calculate the equilibrium constant, so the Ka for hydrozoic acid, and then 2, write the equilibrium expression. So the equilibrium expression, right, would be right here. So you don't have to write the P over R, I just do it as a reminder, but this would be the equilibrium law expression. All right. we've got a follow-up to our question here. So based off of the Ka, so this number that we calculated above, complete the following statement. Hydrozoic acid would be either a stronger or weaker acid than acetic acid because it has either a larger or smaller Ka than acetic acid. Okay, so let's look up the Ka for acetic acid, and then we can discuss this. And you can find that on page 8 or 9 of your data booklet. Okay, so acetic acid is right here. Now, in this last row, that's going to be all of your Ka values. So this table only contains Ka values. It does not contain any Kb values or any equilibrium constants for weak bases. Okay, so that's an important thing to know when looking at this table. So the Ka for acetic acid is 1.8 times 10 to the power of negative 5. So that's going to correspond with the formula in the acid column. It does not correlate to the formula that's in the base or the conjugate base column. Okay, the reason being is because this is the Ka, so the equilibrium constant for the weak acid, which is the formula in the acid column, not the conjugate base column. So let's write that out. 1.8 times 10 to the power of negative 5. So if we compare this with the number that we got, so both of them are raised to the same exponent, negative 5. Okay, but the Ka for hydrozoic acid is larger because it's 1.9 times 10 to the power of negative 5 compared to the Ka for acetic acid, that's 1.8 times 10 to the power of negative 5. Okay, so what you need to understand is the larger the Ka value you have for an acid, the stronger the acid is going to be. So because hydrozoic acid has a larger Ka, that means it's going to be a stronger acid than acetic acid because of the larger Ka value. All right, moving on to example number 2, we're asked to calculate the equilibrium constant for the base, which is a phenolate ion. So that's C6H5O with a 1- charge. So because they're asking to find the equilibrium constant for the base, they're asking us to find what Kb is. And we're told that we have a concentration of this base, the phenolate ion, of 0.8 moles per liter and a pH of 11.85. So we got to continue this on the next page, and we're going to start it the same way we started the last question. So we do need to handle this with an ice table because we need to figure out the equilibrium constant and because we're working with a weak base here. So how we know for sure that it's a weak base, even though you're not going to find it anywhere on this table, the main idea is that since it's not one of our, if it's not one of your strong acids, or if it's not one of your strong bases, so a strong base for the context of this course would just be a hydroxide ion paired with a metal ion. if it's not a strong acid, if it's not a strong base, then you're going to qualify it as either a weak acid or a weak base. Okay, so in this case, because we're told it's a base, we're going to call it a weak base. So C6H5O1 minus. And because the question doesn't mention that this phenolate ion is reacting with anything, we're going to react it with water. Because since this is an aqueous solution, there's a ton of water around for it to react with. Now, since it's a weak base, I'm going to use equilibrium arrows. So since this is our base, remember protons return to home base. So for predicting our products here, I gotta imagine this just with one extra hydrogen to it. So C6H5OH, and the charge is going to be neutral for that. The reason being is because this started out with a -1 charge, and then it gained a proton, so -1 plus 1 is equal to 0. That's why this has a neutral charge to it. Now for my remaining product here, I'm just going to imagine water just with one less hydrogen because the hydrogen got transferred to the phenolate ion. So then we have hydroxide. Okay, so remember that for modified Arrhenius equations, bases are always going to produce hydroxide and acids are always going to produce hydronium. So that's one way you can double check that you're writing your reaction correctly. Okay, so let's write out our ice table. And I'm going to put a thicker line underneath the equilibrium arrow. Okay, so it did tell us that initially we started out with a concentration of the phenolate ion of 0.8. So I'm going to write that in. Since water is our only liquid, we're not going to include it in our equilibrium law expression. And since the concentrations of our products were not talked about, we're going to put them both at 0 moles per liter. Now for the change row, again, just if we're using this visualization of the seesaw with reactants on the left-hand side, products on the right-hand side, so this ball is going to have to move to the right in order to achieve a state of equilibrium, so quote-unquote balanced teeter-totter. Just remember that equilibrium, like this analogy isn't perfect because equilibrium doesn't necessarily mean you have an equal amount of reactants and products here. Okay, so since the ball had to move to the right, and the ball just represents this concentration of phenolate ions, okay, whereas there was nothing on the product side because both of the concentrations for our products was 0. So that means forward reaction is going to be favored. So we're going to use up our reactants and produce products. Okay. Now for our equilibrium row, again, I'm still using that I plus C is equal to E. So 0.8 plus -x is going to look like this. So 0.8 mole per liter minus x is equal to the equilibrium concentration of the phenolate ion. And then for our products, for both of them, we'd be going 0 plus X is equal to the equilibrium concentration of both of our products here. Okay, so for this question here, because we have been given pH, we can eventually use it to find the concentration of the hydroxide ions. But remember, pH helps you to find the concentration of hydronium. Now, since we don't have that, we can't use this number right now. We can't use it as is right now. But what we can do is we can convert it from pH to pOH, and then we can use pOH to help us find the concentration of hydroxide ions. And we can use the concentration of hydroxide ions to determine what X is, because the concentration of hydroxide ions at equilibrium is X. So I'm going to use pH plus pOH is equal to 14 to convert from pH to pOH. So pH, that was 11.85. So, let's try that again. 14 minus 11.85. So our pOH value is 2.15. All right, so now that we have our pOH, we can use that to determine concentration of hydroxide ions. So our formula for that is 10 to the power of negative pOH. So 10 to the power of negative 2.15. Second function log negative 2.15, enter, 0.00707 goes on forever. And there was no times by 10 to the power of whatever exponent, so I'm just gonna leave that as is. So that is our concentration of hydroxide ions, which is also X. So now that we have our X value, we can write out our equilibrium law expression, plug in our values, and use that to calculate the equilibrium law constant for our weak base. Okay, so remember products over reactants. So I'm going to go the concentration of C6H5OH multiplied by the concentration of hydroxide divided by the phenolate ion C6H5O 1 minus, and we're not including water because it's the only liquid there. So now I'm just going to plug in the values that we had for our products. So both of them were X. And remember, I'm only, because we're talking about the equilibrium constant, KB only applies for the equilibrium row. It does not apply to the initial or the change rows. So then for the equilibrium value for the phenolate ion, that was 0.8 minus X. So now I'm going to substitute in, or actually I'm going to clean this up first and then I'm going to substitute in. Okay, so again, X was at 0.0070, goes on forever, and that's squared, divided by 0.8 minus 0.0070, goes on forever. And I'm running out of room, so I gotta scooch this up a little. So how I'm gonna put this into my calculator is I'm going to go second function answer and make sure to square it, divided by bracket 0.8 minus answer, close the bracket, hit enter, so we get 6.3207 goes on forever times 10 to the power of negative 5. So remember, equilibrium constants do not have units to them, and we need to figure out how many sigdigs. So this number right here has 3 sigdigs in it because it's concentration, so you got to look at the entire number. But this number right here only has 2 sigdigs because it has the letter P in it because it's talking about pH, so you only look after the point for sigdigs. So this has 2 sigdigs. You always go with the number with the least amount of sigdigs, so my final answer has to be in 2 sigdigs. So counting from the left, 1, 2, there's my cutoff line, 6.3 times 10 to the negative 5. And remember, KB does not have any units, or any equilibrium constant does not have any units. Now, just to wrap this question up and talk about what exactly this number means, because it's such a small number, so it's a lot smaller than 1, that tells you that at equilibrium, the reactants are favored. So this is a bit above and beyond what the question's asking for, but it's always good to understand what these values mean instead of just being able to number crunch them. So again, remember that the equilibrium constant only talks about what happens at equilibrium. Okay, if we were to go back to our first example here, this number is also quite a bit smaller than 1. So the equilibrium constant for hydrozoic acid, basically what this means is at equilibrium, the reactants are also favored here.